finishing up, take a look at the last page of our notes. We're going to notice that there is a table of Maclaurin series that you should memorize. Actually, the first three, A, B, and C, are especially common. They show up all the time. The natural log of 1 plus x, actually we did derive that together in our notes the other day. And we did the same actually for arctangent or inverse tangent as well. But it is well worth your while to commit these to memory. Notice that the first three have infinite intervals of convergence from negative infinity to infinity, whereas D and E actually have considerably smaller, between -1 and 1. But just wrapping up, let's do example 5, the very last problem. Approximate cosine of x squared dx to 4 decimal places. Well, again, let's recall that b, the cosine of x, is going to be 1 minus x squared all over 2 factorial plus x to the 4th all over 4 factorial minus x to the 6th over 6 factorial. And, you know, of course, this is going to continue. This goes up to x to the 8th all over 8 factorial minus x to the 10th all over 10 factorial. You get the idea. Well, if I wanted to find cosine of x squared, well, all I'm going to do is replace x squared for x in every one of these terms here. We'll have x squared to the 4th all over 4 factorial. Here's a minus x squared to the 6th all over 6 factorial. We'd have x squared to the 8th all over 8 factorial. Do we need to go out that far? Probably not. But case in point, when we are working out example 5, this integral now from 0 to 1, well, the cosine of x squared, let's just work this expansion out. This would be 1 minus x to the 4th all over 2 factorial plus x to the 8th all over 4 factorial minus x to the 12th all over 6 factorial. Maybe do one more perhaps. X to the 16th all over 8 factorial, and going on forever. But as we would work this out, let's very quickly do an antiderivative. Antiderivative of 1 is x. Here we'd get x to the 5th all over 2 factorial, but we're going to also have a 5 multiplied in there as well. Our new highest power is a 5. A 5 has to come down. Here we'll have x to the 9th divided by 9 times 4 factorial. This would become x to the 13th over 13 times 6 factorial plus x to the 17th all over 17 times 8 factorial. And of course this continues on forever, but we're going to evaluate this between 1 and 0. Using the fundamental theorem, when we replace x with 1, we'd have 1 minus, well, 1 over 5 times 2 factorial plus 1 all over 9 times 4 factorial minus 1 all over 13 times 6 factorial plus 1 times 17 times 8 factorial. You get the idea. Plugging in a 0, of course, wipes everything out. So this is what our integral really is. You're going to notice, thankfully, this is an alternating series. We would like to find our approximation to 4 decimal places. So we have our error to be less than 0.0000 zeros and then a 5. So because we have an alternating series here, our goal is to find the first term, if you would, that would allow us to be smaller than 0.00005. And by the way, if we wrote this in exponential notation, we could see we'd go 1, 2, 3, 4, 5. This is 5 times 10 to the -5th, so we'd need to be smaller than that. Well, this is where we need to take out our calculator and just check and see exactly where this all comes out. So we could very quickly say, well, could it be this 1 all over 9 times 4 factorial? Well, perhaps. Let's see if it works. And we'd say math. We could go to probability, go down here. We could see that this sadly is not small enough. We could say, well, what about the 13 times the 6 factorial? Perhaps that would work. We could say second enter, bring that back, and insert right over here, perhaps a 1, and then just type in a 3. Actually, delete that right there. 13 times 6 factorial. Is this enough? Well, not quite enough. No, sadly. So let's see, our next term would be 1 all over 17 times 8 factorial. Perhaps that would do it. Hopefully it will. Let's see. You might need to just spend a little bit of time in search of this. Thankfully this is. The 1 over 17 times 8 factorial is less than that. So what we have is this term is the first time that we're going to be smaller than 5 times 10 to the negative 5th. If we add up all of this, we will get our sum accurate to 4 decimal places. So really what you could do, honestly, is just type this all in on the calculator, doing it step by step, rather than even try to calculate it with the sum sequence. It's probably just as quick to do that. Now 2 factorial, by the way, is a 2. You could definitely save time with that. You could say the next one is plus 1 divided by, and this is where we have 9 times 4 factorial. Well, 4 factorial, 4 times 3 times 2 times 1, is actually 24. So you could save time with that. Finally, we'd say minus 1 divided by, and maybe here at this point, you'd want to type in 13 times your 6 factorial. And what we have as this sum now, you can see that going off to 4 decimal places, we have 0.9045. So 0.9045. Just to bring something up to you, and you might have noticed that I had this typed in actually at the very beginning of our lesson, right when we called up the calculator for the first time. I did work this out with an FN int. You can see we're actually remarkably close to what the calculator is giving us. And if you notice here, we're only using 4 terms in the series. So that's really what we're doing today. I hope this is making sense. Best of luck to you.